Section 3.1 is our introduction to determinants. Now we've already seen a determinant for a 2x2 matrix, so we'll extend this idea to n-by-n matrices and not just have a 2x2 matrix determinant. If you recall that for a 2x2 matrix, the determinant are given by A1, A11, A12, A21, A21, so something like this, A11, A12. All right, this is our matrix A, 2x2. Its determinant, it's kind of visually seen as multiply these two terms together and subtract the product of these two terms together. And we end up with the expression that we see right here in the formula. Unfortunately, this doesn't work for general n-by-n matrices. It's not simply a matter of multiplying along diagonals like this and taking differences. So we'll have to build this out in a more careful way. So one thing that the determinant will help us do, if you remember that when we looked at the 2x2 case, if the determinant of a 2x2 matrix was non-zero, we saw previously that the matrix is actually invertible. And this is an if and only if statement. Remember, that was because, in part because the formula for the inverse of a 2x2 matrix involved this determinant in a denominator. So of course, if this term was zero, this determinant was zero, then our matrix would, or we'd have division by zero, and our inverse would not be well defined. And also we had some flipping of terms here and some negating of terms in the off diagonal. That was all in the formula for the inverse of a 2x2 matrix. It turns out, and we'll see this later on, perhaps not this section, but if a determinant for an n-by-n matrix is non-zero, then we'll see that A will be invertible, or that the given matrix will be an invertible matrix based on that. And it won't be invertible if the determinant is zero, but we'll see that result later on. So what we're really looking to see, well, I guess we'll at least get a hint at it, but we won't formalize it as a theorem until later. But if A is invertible, if and only if it has a pivot position for each row in its echelon form. So that kind of motivates what we're going to do. And it kind of steers us towards a determinant somewhat accidentally, possibly. If we were to put this 3x3 matrix, and this would look similar for 4x4 or any n-by-n matrix, we'd at least come up with the same pattern for calculating a determinant, into a reduced echelon or at least row echelon form to see whether or not it has pivot positions. Then we would move down this column and zero out A21 and A31 underneath A11. And that, of course, is assuming that A11 is non-zero, so that it is a leading entry in the first column. And A22 would be the leading entry in the second row, and we'd assume it's non-zero, and we'd zero out below it. And if it wasn't, then we'd swap out A32 and place it here. But we would, if we're going to have in-pivot positions, we'll need our in-pivot positions along the diagonal of this matrix, right? 3 pivot positions in this matrix means we need to have them in these 3 positions. So we'd have to assume that this all holds. And what those things look like, remember, we're going to zero these 3 terms out using multiples of row 1, and then to zero out the bottom. The third row will use multiples of row 2 potentially. And there's a bit of work to that, and it gets a little messy because these are being done in general terms. Maybe one step I can show you is this. It's intermediate to what we're going to see on the next page. This is row 2 is equal to itself minus, row 2 is equal to itself times A11, but minus A21 row 1. So what we're doing is we're making a common multiple of A11, A21 for that first column term to get rid of the A21 term that's there. The other way to think about it is that maybe we would divide all of row 1 by A11, but that's a little bit messier looking, and it won't give us an easy interpretation of what happens down below. So A11 times row 2, and then minus A21 times row 1. Well, that definitely zeroes this out. And we'll have, let's see, A11, A22 minus A21, A12. That's that entry, and we're getting a little bit crowded here. So let's see this with a little bit more space. And this is A12, and then A13 is A11, A23 minus A21, A13. Remember, everything we need to know about what we've done here is taken care of in these annotations right here. So this is, and we could do the same thing, and we'll see in just a moment. We'll do the same thing to row 3, or a similar thing to row 3. A21, and instead we'll use A31 times row 1, and we end up zeroing this out. But really, this is just an intermediate step. And all the details of this can be found in the textbook, but we at least see where we're headed. We're doing this for a general matrix, so it does make it a bit of a mess. We've got A11 times A31 minus, oh, this should actually be A11 times A32 minus A12 times A31. Similarly, A11 times A33 minus A33 times A31. So that's not the full set of steps. We're trying to get into row echelon form, of course, and we make assumptions like this is non-zero, this is non-zero, and then at the very end, we still need to get rid of this term, but we can see that's going to be quite a bit of a mess. But if we do carry out the details, we get something, we get a matrix that looks like this. And we have this A11 times delta. These terms should look familiar. We just did at least that step. But then zeroing out this term that I pointed out on the previous page leaves us with a leading entry right here, in which we see that we have A11 times this long string of multiples right here. And this is just grouping some similar terms and rearranging some things to get a capital delta that is this expression right here. Well, we've already restricted that A11 not be 0. So, and we could have, we would have done a similar thing for this position as well and swapped out anything below it if it was 0. But the key result now is that this last term here actually be a leading entry, right? So we need delta to not be 0 in order for a pivot position to be in all 3 of these. What you could do is check if we assume that A11 is non-zero, and that if delta is non-zero, what does it say about this term? That might be something to look into, but there might be an intermediate assumption that has to happen along the way. You just have to check the details for it. But nonetheless, at the very end, we're left with this one last delta that if it's non-zero, we know that this thing will have a pivot position in all 3 rows, and therefore the matrix will be invertible. So that gives us a motivation for what a determinant should be in a 3x3 matrix. And in fact, it should be this expression right here. So that's the way we'll define it. Now, if we start to rearrange the terms a little bit, we realize that in this expression, A11 and the other A11 has these 2 pairs of terms, A23 and A32 here, and A22 and A33. Well, if I go back and look, if I'm in the A11 position in my original matrix, so let's go back here. I'm in this A11 position. there's this submatrix that's sort of outside the row and column of this A11. We look again, the next page, there's this A21 or A12 position entry. And note its determinant is this A21, A31, A23, A3, A33. And so that's the A21 position. And then outside of its row and column, we have that same exact matrix that's a 2 by 2. So what we see is by just a little bit of a clever grouping of these terms, we actually have, we move along the first row and we happen to have a plus or minus sign change along each of these, but we're able to move along each of these rows. And it turns out that this is the determinant, the 2 by 2 determinant of what we'll later go on to call the cofactor matrix or the adjoint matrix. So that's a nice, or the matrix minor, sorry to use the correct term, matrix minor of the position A11, A12, and A13. So we get this little bit of a subnotation, and this gives us a hint at the recursive definition for a determinant. So the way we'll work is pick a row. It looks like we're going to use the first row in most of these cases, but that's the one we've demonstrated. But you could do this along any row that you like. You could even do it along a column. We'll see that later on as well. But you move along that row or column and you calculate these subdeterminants and times their minor complement position. So A11 and the subdeterminant of its minor matrix, A11 given as capital A11 here. So now if we had an n by n matrix, we could just continue to do that recursively, right? We could continue to break down until we get to 2 by 2 subdeterminants, and then we know how to calculate those subdeterminants, and that gives us an algorithm for calculating any one of these. This is a sort of our catch-all expression for calculating the determinant of an n by n matrix. And we see there's a parity going on. -1 gives us parity, which is plus or minus for each of these positions. And if we take a look real quick, see that the sum of I and j here, 1, 1 is 2. Here, 1 and 3 is 4. Those are even numbers. We have positive signs here in front of each of those, at least in terms of their own values. And there's a minus sign that slips into this formula because 1 and 2 is 3. So here's our parity term, -1 to the I plus j. The rest of this formula is exactly what we see above in the notation. So there's our initial determinant formula. We will get a different one we can use, but this one's not a bad way to go about computing a determinant, or at least beginning to understand one. So find the determinant of the given matrix. So be a pretty straightforward scenario. The determinant of C is equal to, we're going to move along the first row, just like we were suggested to in the previous formula. And I'll do -1 times the determinant of, in our matrix here, -1's minor is the matrix that occurs by putting together the entries in their sort of arrayed order that are not in the same row or same column as that entry. So 3, 3, -2, 0. 3, 3, -2, 0. And then there's a minus sign here for the second term, or the position 1, 2, right? Really the way to think about it is alternate plus or minus signs. The reason there's a -1 here is just because that was the entry itself. But we force a minus sign into the formula here because, well, thanks to the formula that's dictated to us. So then we've got 0 times the determinant of, and well, we know this is all going to be 0 anyway, but let's have a quick look. There's the column we get rid of, there's the row we get rid of. The matrix minor of this position is 4, 3, 5, 0. Reading rows 4, 3, 5, 0. Position 1, 3 is even parity, so it has, or positive parity is the other way to think about it. So it's a plus sign in front of it. Whatever the number in the position is might change that, but there's a plus sign in the formula. And we have 2 times the determinant of the matrix minor of this position is 4, 3, 5, negative 2. So here we are applying our n by n determinant. In this case, it's a 3 by 3. For 3 by 3, in one step, we arrive down at subdeterminants that are 2 by 2. So that's a quick, easy step down into a quick calculation. So we have negative 1 times 3 times 0. Remember, we moved diagonally, and then minus 3 times negative 2. So this leaves us with 0 minus negative 6, and then minus 0 for this expression, and then plus 2 times 4 times negative 2 is negative 8, plus or minus 3 times 5 is 15. So we end up with, looks like a negative 1 times a positive 6, plus a 2 times negative 23, and we end up with negative 6 times negative or plus negative 46, and that leaves us with negative 52. So the thing we can note is that this determinant is not 0. That's good news. And that would mean that this matrix is invertible. So you could seek out its row echelon form to confirm that if you like, but we'll see in a later result that these things do all connect. Let's see if we can come up with a better way to calculate determinants potentially. So we'll talk about this idea of a cofactor. The cofactor is a value, Cij, based on a position Aij in our matrix A, or an entry Aij, or an element in that matrix in row I, column J, and it's equal to the parity term, negative 1 to the power of 5 plus j, times the determinant of that submatrix Aij, or the matrix minor Aij. So a nice connected rule to this, or once we define this cofactor, it gives us a nice tool for putting together a determinant along any row or column that we might choose to move along in an n by n matrix. And we're going to use this down below. So the determinant of an n by n matrix can be computed by cofactor expansion across any row or down any column of A. So this just frees us up to calculate with the cofactor, which is essentially, when you look at it, no different than what we defined on the previous page. So though that part's different, this theorem allows us to move along a jth column or an ith row or whatever it is we think is most useful. We notice on the previous determinant that we calculated, we had a 0 in our row, and that actually worked out really nicely. We were able to calculate at least one of those terms really simply, because that 0 just zeroes out that determinant factor. So the tactic now will be to choose either a row or a column that puts the most number, that has the most number of zeros in it, and that'll really simplify your calculation. So in this case, we're looking for the determinant of this matrix C. Let's try expansion along a column. What does that look like? So I'll have 0 times the determinant of, and this is this position, I'm going to go along column 3. And they ask us to do that anyway in the instructions. So my matrix minor is 2, 4, 0, negative 2. Now I'm just writing that down just for the practice of it, because I know that overall that's going to be 0. Then minus, that's by the formula for the cofactor. And I have negative 1 as my constant in this position. Its minor is 1, 5, 0, negative 2. And then lastly, I have a 0 times the determinant of, and just for one more round of practice, third column, third row are out, and my minor is 1, 5, 2, 4. Now the only one of these that matters is the one with the non-zero value in front of it, and that's a negative negative, negative 1. So there's a 1 times this negative 2 minus 0 determinant. That's all from this term expression. So we have 1 times the negative 2, and we get negative 2. It's a nice quick way to do that by cofactor expansion. At least just gives a little bit more of a name to what it was we were dealing with in the original definition. So if we have any triangular matrix A, triangular matrix, also square matrix, n by n triangular matrix. Remember, triangular means it has zeros below the main diagonal. Then the determinant of A is the product of the entries on the main diagonal of A. So the intuition for this proof is to write down what a triangular matrix looks like. We've got A's, possibly zeros along the main diagonal, but I've called them A11, A22 through ANN here. And then possibly non-zero, possibly 0 values above that, but definitely 0 values below this. If we think about how to compute this matrix determinant, well, let's expand along the first column, because then we only have to think about one determinant that survives along this column in the cofactor expansion, and that's A11's A11 times its minor, or its cofactor, which is the determinant of this submatrix, A22 through all of that. Well, then A22 below it is all zeros. So we would expand along A22's column, right? So then we just expand along that, and the only one that survives is A22, and then times its matrix minor. And as we proceed through this, we realize that the only multiples that survive this process are A11, then A22, and so on, up to AN minus 1, AN minus 1, N minus 1, the position right above that along the main diagonal. And then lastly, we'd have the determinant of, well, we probably would have stopped before we got here. So maybe I should write this as something a little bit more informative. We actually would have stopped at AN minus 2, N minus 2, because this last determinant would have been a 2 by 2. It would have looked like this. We would have had A n minus 1, n minus 1, and then whatever this term is A n minus 1 n for the nth column. And this is a 0 below here, and this is A n n. And we realize that both of these terms are going to be a product minus 0 is the other product this way. And they're all times all of the terms that we picked up along the way. So it's this sort of nested set of determinants that gives us this result. So if we happen to have a matrix that's in echelon form, then we can compute its determinant just by multiplying along the diagonal. And really the main idea for that is just using cofactor expansion along all the 0 columns. So that's our brief section 3.1 introduction to determinants. We're going to see some properties of these things in 3.2 and then some nice applications in 3.3.